We are continuing our road to master AI research and engineering. So this is episode 3 and just a quick intro. So it's more important, way more important to understand current things, to understand mathematics than to read 1,000 new AI papers. Look, here we have some vectors and they will just rotate. So they will not stretch or squish, they will just rotate. So these are the vectors here. X-axis 3, y-axis 1. And 1, 2, and minus 2. So if you check, those are all of the vectors. They are right there. And then we will multiply each of those vectors with this matrix. So we will say this vector times this matrix goes like this. So 3 times 0 plus 1 times 1. That's going to be our x-coordinate, new x-coordinate of the vector. And 3 times minus 1 plus 0 times 1, that's going to be our y-coordinate of the new rotated vector. So matrix is going to rotate the space, and the space will pull the vectors as well. But check this out. If I put number 3 here, check out what happens. The space gets stretched, and it pulls all of the vectors. I don't know what this microphone sound is. I'm trying to fix it, but I don't know what's happening. But if the matrix has normal rows or orthogonal rows to each other, so this vector, if you look, this vector is like this, and this vector is like this. So they are 90 degrees, they are normal to each other. Then the transformation will just be rotation or reflection, but it will not get stretched or squished. Here we have reflection, so let's see. The vectors stay same length, it's just that they get reflected around. But these squares stay squares. So that's this matrix, it's orthogonal matrix. So it will just rotate or reflect, and we need for later to understand what orthogonal matrix is. Now let's learn the next thing. If we have a matrix with rows that sum up to 1, let's see here what happens with this matrix. If I play, it's going to squish onto a single line. And in this case, that's going to be a problem. And this is just in this case, not in every case where rows sum up to 1. So just this particular matrix. So why is it in this case? It's because if you look what happens, if you have a vector xy and you multiply with this matrix, you basically lose the y-coordinate completely, and both of the coordinates become x. So in this case, you lose one dimension, and there is no way for you to know where how to get it back, because whatever y is, it will always gonna be multiplied by 0. So there is no way to reverse it. You don't know where it came from. So you can know that this will happen just by looking at this matrix where this row is same as this row, or it's just multiple of each other. So if this was 2, 0, then you would still lose y. Or if this was 1, 1, 2, 2, then you would still lose information because the second row is a multiple of the first row, so they are linearly dependent. So you would still lose information. This is another example. This is not adding up to 1, but I want to show you what linearly dependent rows mean. So 1, 2, and 2, 4. So this is just 2 times this row. So they are linearly dependent. And let's see what happens. They're going to get squished onto a line again. So they lose one dimension because there is just one linearly independent dimension here. So we will have a line that's just one dimension of the coordinate system. So in this case, if you do some math, you will find this criteria where every x and y coordinates, every vector that has the same result when you say x plus 2y, any x and y that have same result will map onto the same spot. And there will be infinitely many of those for every point on the line. So for example, if you have 3 and 2 and minus 1 and 4, both of them will map to 7, 14. Look at these two small vectors, they're gonna map onto the same point here, same point. So if you want to multiply that point with some matrix to get the previous vector, well, there is infinitely many. There is no matrix you can multiply with to get the previous vector because there is infinite previous vectors that are all different. So it lost information. So the point with making all rows add up to 1 is very simple. Let's see if we have some huge number here. This is what happens in could happen in neural network. We have some explosion of some number. So this can make training unstable. So now it's gonna stretch this extremely a lot. Now I'm gonna try to explain this. I don't get it 100% either, but we will figure it out. So this is what happens when you train neural network. Let's say you have weights and you did the gradients. So now you want to update neural network weights to minimize the loss. So this is going to stretch the weights or update some direction a lot more than other directions. And at first I thought, well, if the gradients calculated that this is the best way to minimize loss, then let it be. Let's update in this direction to the big extent so the loss will get a lot smaller. But in reality, the gradients don't need to be big just because loss gets smaller in that direction. They can also be big because input features are huge. For example, if we say cat and dog and lion, and if we say, okay, cat is number 1, dog is number 2, and lion is number 1000. And now we plug these numbers and we want to calculate gradients with them. Just because this number 1000 is huge, then the gradients will be huge in some way. Just because they got multiplied with a huge number, not because the loss is gonna go down more or become better. I don't know how to animate this. I'm using this software for the first time, so maybe in the following videos. And ChatGPT explains the same thing. As I said, if we have input 1, 2, and 1000, and each of them is multiplied by some weight 1, weight 2, weight 3, and let's say later they are all added up or multiplied with other weights or something, and so in the end we have some result, whatever. So as you change this weight that multiplies number 1000, if you change it just a little bit, because it's multiplied with number 1000, the change on the result will be huge. So this weight has huge influence, and then when you calculate the derivative, the gradients with respect to this weight, you will notice that if you change this weight a little bit, the result change is big. And this is just because it's multiplied by a huge input number that's arbitrarily chosen. Not because like the gradient here, if you change it, it actually improves the performance. It's just because the input number is huge in comparison to these other input numbers. Of course, you will not choose such ridiculous inputs, 1, 2, 1000. But whatever input you choose, there will be some of this scaling just because the numbers are bigger. So you want to neutralize this issue as much as possible. So we can do that by normalizing everything, normalizing weights, normalizing updates. So in this case, we are talking about the update matrix that's gonna transform our weights after the backpropagation. So we have this matrix, and if we multiply our weights with this matrix, then our weights will become more accurate, so they will later give better results. So that's the update matrix. And we get this update matrix by doing the backpropagation and figuring out how much the loss changes with respect to weights and stuff. So we'll learn more about this if it's a bit confusing, but basically we want to make all of the rows sum up to 1. So in this case, this row will absolutely dominate this row and every other row. And this row will stretch the entire space and everything hugely, insanely. And the other rows are not going to make a bit of too much change. But if we make them all add up to 1, so this will be like 0. So let's see these rows, 2 and 1000. So this vector is almost on the y-axis from 0 to 1000, almost. It's just a bit of an axis, x-axis to the right. And this second vector is 3 minus 1. It's like this. So they are not 90 degrees, they are not orthogonal. So first of all, the length of this upper first vector is insane, and they are not orthogonal. So after our Muon optimizer, the new Muon optimizer uses Newton-Schultz method to process these vectors, they will become 0, 1, and 1, 0. This is close to 0. So don't look at these calculations. These are different method, not one that Muon is using. But anyways, as you can notice, these vectors are now like this. They are, first of all, their length is 1. Not some of these coordinates is 1. In this case, it's accidentally 1, but the length is 1. So if you take Pythagoras theorem or if you take the norm, it's going to be 1. And they are 90 degrees. They are orthogonal to each other. So this is called orthonormal. Length is 1 of all of the rows, and the rows are perpendicular to each other. So this will not have these insane huge values that one direction gets stretched. This will make all of the directions, all of the vectors, all of the rows pull equally. So they found that this converges better than if you have these huge, arbitrarily huge numbers that are not huge because they reduce loss, but because simply of the multiplication with some huge inputs or some other reasons. Guys, I will probably be able to animate all of this in one of the future videos because I don't know how to do it yet. So to recap, benefits and drawbacks of the new Muon optimizer and maybe future research directions. So it's just gonna make all of the rows, the vectors, pull equally into every direction instead of one row pulling too strongly, not because it reduces loss, but because it go just multiply with big input numbers or big numbers. So, but the issue with this, actually, maybe some rows, some vectors should be a bit stronger, a bit longer than the rest to make the loss go down faster. Okay, so that's maybe the research, future research direction. How do you actually distinguish between vectors being longer because they got multiplied with huge numbers as opposed to being longer because they actually reduce the loss better? So maybe whoever works on this could bring the next 2x speed up to AI training time and AI progress. And then how Muon is doing this is a different story. It's using these Newton-Schultz iterations, but we will learn about that in one of the future videos. So that's it for this video, and see you next time.